Okay, so welcome everyone to the Students Colloquium of Sci-Fi. Today we have with us Soumya Sarkar. Soumya did his bachelor's from Bidhannagar College and currently he is a master's student at National Institute of Technology, Karnataka. Today he will be talking about restrictions in quantum no-masking theorem. Now before the talk starts, I just want to say a few comments that keep yourself muted and we will take the questions at the end of the talk. So without further delay, over to Soumya.
Thank you. Good evening, everyone. So, my name is Soumya Sarkar. As I'm introduced, I'm currently studying pursuing my MSc in NIT Karnataka. And so, last summer in 2019, uh, I did a project on quantum no masking theorem under the guidance of Professor P.K. Panigrahi in either Kolkata. So, in I did this work based on the paper uh, written by A.K. Pati, Kavan Modi, Ujjwal Sen, and 2018 Sharu Bhatnagar awardee uh, Aditi Sende. So it was recently published back then in the later part of 2018, I guess. So moving ahead. So this is our paper. Uh, it is not it's not peer reviewed yet. We have applied it to Springer. Let's see what happens. But it has got 7 citations. If you are people really interested, you can read this paper. It's available in ResearchGate and archive. So, so in this presentation, we'll first see uh, why the masking of data masking is important in, in quantum cases. So first we'll see the classical analogy to have the better understanding of the topic. And to start with, we will see some important we'll see some definition of some important terms, and then we'll one by one we'll see our motivation of our work, then our work in details, and some new restrictions, and then we so moving ahead, why it is important. So in 2016, a study told that above 25% of data breaching was happened due to the employees of a company itself. So the employees are not trustworthy. So if let's assume if you are a CEO of a company, and uh, so you don't like you have the whole database of the company, and you don't want to share all the database to your among your employee because they are not trustworthy, because there is always a chance that the data is breached by your employee. So what you basically uh, give an access to your particular employee to some particular portion of data of your whole database, right? So to a particular employee, you give a particular portion of the database, so he can access to that particular portion, and the rest are masked. So this is how you can control your employee, that how he can when he can access the data, and how much data he can access. So this is where data masking is important. So what is it basically? Yeah, the actual data is not transformed. It is basically what the name suggests it is just a cover, or replacing the actual data with a fake data. So there is a common misconcept among the common people, that data encryption and data masking are same, but they are not, because in data encryption, the actual data is transformed using some algorithm or some key distribution. So it is totally transformed to a new data form. But in the case of data masking, the format is preserved, and unlike data encryption, it is not reversible. Like in data encryption, you are using a algorithm or key distribution to encode the data, and you need that key distribution data. You have to know that particular key distribution to uh, decode that data to know the actual input. But in case of data masking, you can't, like if you are not if your data is masked from you, then you can't can't decode that data and know the actual data. So uh, 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 common question arises that what is more safe, data encryption or data masking? It is not about what which is the safer method. It is basically a two parallel methods to make your data safe. In different purposes, you need different methods. In some purposes you need data encryption. In some purposes you need data masking. So, uh, so it's simple that you want to disguise something or keep others from seeing it clearly. You mask it. So it's nothing about even about transformation or something else. You just mask it so that one cannot see your actual data. Okay. So now the classical analogy. So you see that when you when you typing a password, when you're typing a password or a pin code, as soon as you write, as soon as you type a character or a letter, this is replaced by some asterisks, by some dots, or some anything else. Okay, so this is the classical analogy of masking. That if you are typing a password, no other people can see your password or your pin. So there are lots of other methods to mask your data in classical classical data. But this is one of the easiest examples which can show that data masking is happening. So to start with, we will see some definitions of some important terms to follow the presentation. First is no-go theorem. So there are lots of no-go theorems like no cloning theorem, no deleting, no broadcasting, and etc. So no cloning theorem basically tells you that in classical computers you can clone or copy your files or folders from one place to another place easily. But in quantum computers you can't clone any arbitrary quantum state. Right? There are some exceptions, but in general you can't clone our data or a quantum data. And no deleting theorem is just telling you that like no information can be deleted from this universe. So information is preserved. And no broadcasting theorem is just the generalized version of no cloning theorem. No broadcasting theorem, you can clone a data, arbitrary quantum state, and broadcast it to multiple multiple uh, people or systems. So in 2018, there is a new addition to the list, the no masking theorem. So it basically tells you that unlike classical computers, uh, you can't mask a quantum state, arbitrary quantum state in quantum computers. This is the claim of that paper we worked on. And then the density matrix, it is basically the sum of the projectors weighted with the appropriate probability. So you have a wave function psi, which is basically the summation of the basis vectors, summation of Cn and K of basis vectors. So you take the outer product of that, and you have the matrices where each elements of that matrix represents uh, the probability amplitude or the coefficients of each of every combination of your basis set. So from a density matrix, what you can do from a density matrix is this composite system where there are more than one subsystem. You can extract the information about the subsystem from the density matrix. So here is partial trace. Partial trace is uh, if there is a composite state system, so you calculate the partial trace you use this calculation to extract the information about the subsystem from the density matrix. So same as calculating reduced density matrix. So from calculating by calculating partial trace, you actually calculate the reduced density matrix. So this reduced density matrix represents the the information about the subsystem. Now the distance and fidelity. What is distance? Distance is the difference between two matrices. Here the formula is like this. So here is rho t, a density matrix, and rho is another density matrix. So what you do, you take each element and subtract and make a summation and divided by 2, and you get the distance. Okay, so these are the elements, each elements of rho t, and these are the elements of rho e. So the greater the value of the distance, the greater the difference between two matrices. And the fidelity is the measurement of similarity between two matrices. So you have two matrices, rho and rho t, and the formula is like this. So fidelity will tell you that how similar two matrices are. So if the value of fidelity lies between 0 to 1, if the fidelity value is 1, then the two matrices are exactly similar. If it is 0, then they are exactly similar. So moving ahead, this is a screenshot of an example. I have taken it from the book written by Professor Onivan Pathak. So here you will calculate the partial trace out the second qubit of the 2-qubit entangled state 1 by root 2 0 0 plus 1. This is the composite state. So the first qubit here and here uh, you can say this is the subsystem A, and this is the second qubit. So you want to trace out the second qubit. So first you will calculate the density matrix, as I've already told, the outer product of that wave function. So this will give 1 by 2 and all the combinations of the outer product. So and then you compute the partial trace as trace B of rho. So what you do, you operate this trace B on these four outer products, and as you are operating this on subsystem B. So the first subsystem came out from that trace operator, and it is operating on second subsystem, and it turns into inner product. So trace on the outer product turns into an inner product. Here 0 outer product turns into an inner product. Here 0 1 turns into 1 0. Here 1 0 turns into 0 1, or 1 0, same thing, and 1 1 to 1 1. You can think it in another way, that you just take the normal trace. So 0 is basically column matrix of 1 0. So you take 1 0 multiplied by row matrix 1 0, and you have I think 1 0 0 0, and you take the trace. So you will have 1. So this becomes 1 because 0 and 1 are mutually orthogonal, and 0 and 1 are orthonormal staples. So this is 1. These 1 0 are orthogonal, that's why it becomes 0. This will go out, this will vanish, and this will vanish, and these two terms will remain. So half 0 0 and 1 1. This is how you calculate the partial trace. Right. So our motivation was so it was a new no-go theorem in the market. So it needs to be verified experimentally. That was the theoretical paper. So we verified it experimentally on the IBM quantum computer. So we basically focused on the exceptional cases. So in general, they claim that in general masking of quantum information cannot be possible, but in some non-orthogonal cases, non-orthogonal set of states, masking can be possible. So we focused on the exceptions and restrictions where masking is possible. Okay. So as a just first graduate student, wonderful opportunity to increase the exposure, and topic was totally new to me. It is still now new to me. I am learning still, but at that time it was totally new and obviously. So our work is uh, to to map the quantum information into different types of quantum states. So we have taken 4 states: first orthogonal quantum state, non-orthogonal quantum state, arbitrary quantum state, and tripartite. So first 3 states are bipartite and two-dimensional system. So what is bipartite? Bipartite means there are two subsystem, and two-dimensional system means there are two gates are there. Two gates are there. So yeah, we work with these states, and then tripartite system where there are uh, three subsystem, and this is still a two-dimensional system. Now we'll calculate all the partial traces and calculate the fidelity and distances for each case. So you will understand in a minute that why we will calculate all the partial traces and calculate the fidelity. So moving ahead. So what was the expectation from the 2018 paper? The expectation was that for some non-orthogonal states, masking is possible. For orthogonal state, masking is not possible. For arbitrary quantum state, masking is not possible. And for tripartite system, masking is possible. So not only tripartite system, but anything greater than bipartite system, any multipartite system, in the case of any multipartite system, masking is possible. So these are the expectations. For non-orthogonal, masking possible. For this, not possible, not possible, possible. Okay. So this is what is it like mathematically. So this is the condition of masking when the quantum masking will happen. So this is the psi is your wave function where you are masking your information into. So this is a composite system where there are two subsystems A and B, and you take the outer product of it and calculate this basically the density matrix, and you trace out the for both subsystem, and you get reduced density matrix for A, for subsystem A, and for subsystem B. So for masking to be possible, this row A and row B must be identical. So what does it mean? If the information in row A and row B are identical, then a third party won't have any won't distinguish between these two subsystem, and eventually he can't know the actual input, right? So you have let's assume you have psi is equal to alpha 0 psi naught and alpha 1 psi 1. Okay, so you don't have the information about this k, right? So if they are identical, you don't have the information about this k, whether it is 0, whether it is psi 0, or whether it is psi 1. So you can't distinguish between the information about the information of subsystem A and subsystem B, and eventually you can't really know. You have the data, but you don't have you don't have okay. So you have the data, but you don't have the information, right? So there is a little difference between data and information. So data is basically the things you have, but information, if the data is informing something to you or is useful to you, then it is called an information. Okay, so not all data are called information. Uh, so this will remain a data, but not an information. So you can't basically you can't know the actual. So for each case, we will calculate the fidelity and distance between these two matrices. Okay, and if the fidelity is 1, so it will never happen. It will never be 1. It will tend to 1. If it is tending to 1, then masking is happening, because if fidelity tends to 1, then the row A and row B are almost similar. Okay, then masking will happen. Masking will be possible. And if distance is 0, means that is there is no difference between row A and row B. So masking is happening. So this is the mathematical aspect. So in a nutshell, you have information, and what is information in a quantum set? The probability amplitudes, that is the coefficient. So you can control the probability amplitudes by applying different magnetic and other things. So you have the information, you are mapping it into different quantum states. In our case, there are 4 quantum states we have considered, like non-orthogonal state, orthogonal state, arbitrary bipartite state, and a tripartite state. Now we map those into some quantum state. Now an intruder tries to extract the information from the state. Okay, so uh, he or she will calculate the density matrix, and then they try to trace out and make the reduced density matrix, and that basically reveal the probability amplitudes or the information about the subsystems, right? So, but it turns out to be the same or identical. If masking is possible, then it turns out to be same or identical. Means the information about the information of subsystem A and the information of subsystem B become identical. So, so he or she couldn't distinguish the data and know the masked information, the actual input. In short, you would have the data but not the information. I have already mentioned that you will have the data but not the information. So can we choose any random state for performing the masking information? So if we are considering 4 states. Okay, so can we choose a random state for performing masking of information? So the answer is not really, because this is one of the restrictions that for a bipartite system, there are basically 16 combinations can be possible, but you can see that there is some overcounting. 0001 and here is 01 and 00 are basically same. This one and 0010 and 1000 are basically same. So there are kind of overcounting here. So there are combinations out there, but we can choose only these much states. Okay, because only for these states, first thing is that you have to choose the non-orthogonal state and orthogonal state, and secondly you have to fulfill the uh, masking condition first theoretically. So only for these 4 states, not 4 states. Here also you can see overcounting 1100 and 0011 are same, and 0110 and 1001 are same. So for these states only you can theoretically fulfill the masking condition. So we can only choose these much states for our experiment. So this is the psi and alpha psi 0 and alpha 2 psi 1. So what do we mean by orthogonal state and orthogonal state? We mean that this psi 0 and psi 1 will be mutually orthogonal or mutually non-orthogonal. Okay. So next, now let's see one by one the masking of the quantum information into each state. So it's kind of boring stuff, same thing for each state. So this is the circuit of the carrier state. So where we are masking our quantum information into. So this is the circuit of a non-orthogonal state. The states are basically psi 0 is 0 plus 1 1 by root 2 and psi 1 is 0 plus 1 1 by root 2. These are basically the entangled state in perfect, the maximally entangled state. Okay. So actual wave function becomes this 1 by root 2, 0 0 plus 1 1 by root 2 and I by root 2 and 0 plus 1 by root 2. So this circuit is just a representation of 0 0 plus 1 1 by root 2 only. Okay, this 1 by root 2 and I by root 2 are your information. So you can apply you make any get or you any get, and you can change this 1 by root 2 and I by root 2 according to your will, but obviously maintaining the bond rule, that is alpha square plus beta square is equal to 1. So uh, so first you have to, like as I already told, that you have to fulfill the masking condition theoretically. So what you do, you will calculate the trace A psi 0 and trace B psi 0 psi 0. You will just calculating the reduced density matrix. So they are basically same, 1 by 2 0 0 plus 1 1. So the masking condition is fulfilled. In this case also, if you are this is the psi 0 case and this is the psi 1 case. So for two cases, the masking condition is fulfilled. Okay, so we can go with this step. So this is a very trivial step. So so that's why you can have the distance is exactly 0 and fidelity is exactly 1, because as you can see here, you are taking this state and this is exactly same. So you will have exactly same row A and and exactly same row B. So you will have exactly similar to matrices, and that's why the distance is 0, exactly 0, and fidelity is exactly 1. So what do these fidelities mean? These fidelities mean that how perfectly we are doing our experiment. We are performing our experiment. Okay. So we have our theoretical have our theoretical matrices, and we have our by doing these experiments, if we calculate all these and run a code, you will have some experimental density matrices, right? Now you calculate the fidelity between those. So the fidelities are 0.9985 and 0, almost tends to 1. So yeah, almost perfect. The experiments are almost perfect. So these fidelities represent that how perfectly we are doing the work, and this fidelity represents that the similarity, the measurement of similarity between the density matrices of the subsystem, rho A and rho B. So next, the non-orthogonal state, sorry, orthogonal state. So the states are psi 0, 0, 0, 1, 1 by root 2 and 0, 1 plus 1, 0 by root 2, and the final state is this. So in this case also, you can have this state by by uh, by by applying these gates, these quantum gates. In this case also 1 by root and I by root 2, you can choose according to your will, obviously maintaining the bonds too. Now when we calculate the distance, in this case the distance is 0.0527 and the fidelity is 0.9997. So it is in this case also the masking is happening. Okay, so what we saw is that for non-orthogonal case and for orthogonal case, the masking is possible. But according to the paper we worked on, the expectation was that for for some sets of non-orthogonal set, masking can be possible, but for orthogonal set, masking cannot be possible. But here we can see that masking is also possible for an orthogonal state. So what's the catch? We'll see in a minute. Okay. So moving ahead, now we will see the experiment of here we have used the Hadamard gate. Here also we have used in the previous case we have also used the Hadamard gate. So they are not arbitrary, but here we will use the U3 gate. The U3 gate is arbitrary. So U3 gate is represented by cos theta by 2, this element, this element, this element. So if you put theta is equal to pi by 2, lambda is equal to pi, these are the three parameters. uh, you can change the states or the coefficients by changing the value of these three parameters. And if you put theta is equal to pi by 2, lambda is equal to pi, and phi is equal to 0, you will have these Hadamard. So Hadamard is the special case of use. This is the most generalized case for a 2 qubit quantum gate. Okay. So here cos theta by 2 pi here if you put pi by 2, this will be pi by 4, so 1 by root 2. Here you will get also 1 by root 2, because this minus I lambda minus 1 minus 1 plus and 1 by 2 and this and so on and so forth. So you will have this 1 by root 2 comes out and 1 1 1 minus 1. So in this case we will use the U3 gate. This is a mistake. So here it will be there will be U3 gates in the place of Hadamard gate. So uh, for arbitrary case, if you are masking an information in an arbitrary quantum state, we will have that, and if you can calculate the density, distance and fidelity, the distance is 0.6 and the fidelity is 0.8299. So you see the order of the distance. In the previous cases, For the trivial case it was exactly 0, and for the orthogonal case it was 0.05, but in this case it is 0.6, much higher than the the previous cases. And this is also comparatively low fidelity, uh, not much low, but comparatively it is low, because in previous case you are having 0 0.9, above 0 0.9, and in this case you are having 0.83 and so on. So in this case also we are doing our experiment almost perfectly, because the fidelity was 0.949 and 0.1. So the expectation is fulfilled here also, that for arbitrary quantum state you can't mask your information. And now for the tripartite system, so by here is an unitary gate. So by applying this gate, you are basically creating the state 000 plus state 111 divided by root 2. So this is the maximum. This is called the GWZ state. I actually forgot the whole name. So it's called a GWZ state. This is the maximally entangled state in tripartite system. So if we calculate the same way, we have the fidelities. These are the fidelities between subsystem A and B, subsystem B and C, and subsystem A and C. So we are, in this case also, we're having much higher fidelity. So in this case also, in tripartite system, you can mask your information. So this is kind of, we have done this to just support our previous work. Okay, so not only tripartite system, but for anything greater than bipartite system, for any multipartite system, unlike a bipartite system, if you are having a arbitrary quantum state, you can mask the quantum information. But in a bipartite system, if you are having arbitrary quantum state, you can't mask that data. Okay, so this is one difference. So the new restriction, what is the new restriction? So as I told that there is a catch. What is the catch? There is a difference, that in orthogonal case also the masking was happening. So the catch is that, if you if you are having a state psi and calculating the trace, you will have alpha 1 square trace x, sorry, partial trace of x, psi 0, and all these terms. But you will see that to fulfill the masking condition, these two terms should vanish. Okay, so this plus this should be equal to 0, right? Now if you calculate, till now you are calculating this term and this term, as we have calculated the first, I have shown in the first case. I have calculated psi 0 and psi 0, psi 1 psi 1, and they are basically same. So 1 by 2, outer product of 0 0 and 1 1, so they are basically fulfilling the masking condition. But if you calculate these trace psi 0 and psi 1 and trace psi 1 and psi 0, you will see that they are non-zero and they are same, they are identical. Okay, so there is a difference in global phase, but we can ignore that. So basically they are same. This term and this term is same, and this whole term is equal to 0. So as this term and this term is same, we can take out this from the bracket, and write this as trace x psi 0 psi 1 into alpha 1 alpha 2 star plus alpha 1 star, and alpha 2 is equal to 0. So the thing is that uh, it is not only restriction on the state you are masking into, but you have a new restriction on the information itself. What does it mean? That uh, it depends on the information you are masking. You can't mask any arbitrary information. To mask an information, you have to follow this restriction. Okay, that alpha 1 alpha 2 star plus alpha 1 star alpha 2 is equal to 0. So for those cases, for the previous cases, 1 by root 2 and I by root 2, they are basically following uh, this alpha 1, alpha 2 star, and they're basically following this condition. So uh, they were being masked. So this is the catch. So you have to, unless and until, I mean, see, until you are following this condition, your masking method can be possible in quantum computers, right? So in arbitrary quantum state, the coefficients were not following this condition, so they are not masked. So in conclusion, what we can see, that restriction not only on the state we are masking our information into, but also on the information we are masking. So the first restriction I have shown that that from that combination of states we can only choose these four set of states that uh, that are following the masking condition theoretically first. So that was the first condition, but that was not the only condition. The In the previous case, we have seen that there is another condition, that the information you are masking, that should maintain this condition. So there are uh, two restriction. So in general, so it's right that in general you can't mask data in quantum information, but if you follow these two restrictions, you can mask your data. So in general, masking of quantum information is not possible for a bipartite system. Okay, for multipartite system, you can have masking you can have the masking of your quantum information for arbitrary quantum, but for bipartite system you have to follow these restrictions. And the restriction and these restricted states can help the data masking in quantum technology. So for cases when the quantum technology uh, will come into market, you should need some like some safety to to avoid the leakage of your data from a third party. So these restricted states can help your data masking in quantum technology. So this is the application that can be possible in your future. So thank you. One thing I should mention that uh, uh, that these masking, these data masking and data encryption, these all are some parallel methods for making your data safe, and they are not like uh, nothing is more nothing is better or nothing is worse. They are all parallel, and so this is the thing. So thank you. Um, so any questions you can ask.
Thank you, Shoma, for the wonderful talk. So, if you have any questions, then you can raise your hand or write it in the chat box. Um, I can see one question in the chat box. So,
And
if
no
you want to ask, you can unmute yourself.
and non-orthogonal states be made orthonormal or grand scheme conditions, and does the statement about possibility of non-masking a paradox? Well, actually can't understand the question.
Uh,
States be made.
Doipan, you can unmute
Hello,
yourself.
hello.
Yes,
Yeah, yeah,
yes.
Yeah,
now you
Shomo. So my question was, you stated that non-orthogonal states can be we can use to do masking, right? And
Yes.
orthogonal states we cannot. So I
Mhm.
think in quantum mechanics we can.
No, orthogonal state. Okay, orthogonal state we can't
Yeah,
until
that's the
and
question. Like how? Like, I didn't understand that. Could you explain that again?
okay. Okay, so until and unless you are following, you are not following the last condition, that alpha 1, alpha 2 star plus alpha 2, what was that? Alpha 1, alpha 2 stars plus alpha 1 star and alpha 2. You can't, you can't mask your data. I mean, you are if you are following that condition, okay, that restriction of your information, like I have chosen the coefficients as 1 by root 2 and I by root 2, Now if you calculate a 1 by root 2 and I by root 2, there the right hand side and left hand side, they're basically following that that condition. So if you are following that condition, you can have your data masking like whether it is orthogonal state or non-orthogonal state. Okay, does it make sense? So,
Okay. So Anirban, you can go ahead.
So I understand how theoretically you are carrying out the partial traces to check the distinguishability between the subsystems. But experimentally, IBM quantum computer, how do you trace? Like with quantum gates, how do you carry out the partial
so
trace?
basically, if you open the IBM quantum computer, you can have there is some process you have to go through. Like you will have you have to calculate the probability distribution for each like xx, xy, xz, all the combinations of you will measure that state, and you have to have the probabilities for all the combinations like xx, xy, xz, and then yx, yy, yz, and then you have some codes in MATLAB, and you put all that data, and you will have the output states, output density matrices, okay, experimentally, and you can carry out the rest process.
So you don't need any other quantum gate for that. You're calculating it through the probabilities only, right?
So you are applying the quantum gates to build the circuit, okay.
Prepare the state,
Then
yeah.
then you run the experiment, and it will take some 4 to 5 minutes, and you will then have the probability distributions for each cases, okay, that x x x y x z all in all the directions, and you just put that information. So you to get those information, you have to run the circuit, so you have to apply the quantum gates.
Yeah.
So from that you just run the code, and you will get the experimental values of that density matrices, and then you can also calculate the reduced density matrices by pen on paper.
Okay.
Okay. Any more questions? I don't see any hands raised, so I'll just ask one question. That is, you want to apply this masking of data to when quantum computers come in the market, right?
Mm-hmm.
Okay. So do you want to mask the data to avoid any breach of the data? So
Sorry,
in
sir, I couldn't understand.
you want to mask the data because you want to avoid any breaching of the data, right?
Okay, yeah.
Okay. So in classical computers, to have a breach of data, you need to input a malicious program like a virus or something in the computer so that you can extract the data maliciously. But in the case of quantum computer, what sort of program do I need to do that kind of thing?
Okay, so there are some. Okay, I don't know so much technical things, but I guess there are some uh, there are two portion of now the workings are going uh, to two portion. One portion is trying to save the data from the third party, and one portion is trying to hack the data. I mean, uh, the more you try to hack the data, the more you know that how much the safety is. I mean, how much the data is secured or not. So there are lots of other codes also there that are trying to uh, like uh, break the security. And so there are lots of other codes. There are lots of codes that are making your data safe. And also parallelly, there are lots of codes that are trying to make your data that trying to break your data. So there are lots of things are going parallel, so that the actual the actual result came to that you can have a more more safe data, like not there are like yeah, I guess I have told that they're trying to say, does it make sense? I become confused a little bit. So mainly the thing is that there are lots of codes are there in the market, just that are trying to uh, like break your security. So from that, I don't know all of those, but uh, there are codes.
Okay, okay. Thank you. Okay. So, Honorable, do you want to ask something? Because I can see you have raised your hand.
Yeah, I actually want to ask Doipan's
Okay.
question again. I think I
Okay.
feel like it was sort of unanswered still, because I think he means that if any non-orthogonal state can be made into an orthogonal state by orthogonalization, then what difference does it make if we are able to mask a non-orthogonal state or an orthogonal state, right? So
So,
that kind
so
of paradox I think he was talking about.
so you are asking that if there is a non-orthogonal state in your you are making this an orthogonal state, so there is no meaning like that restriction, right?
Yeah, I can make a
Yeah, yeah.
yeah.
So yeah, that might be possible, but I guess um,
Is there some
uh,
loss of information when we are
no
orthogonalizing?
loss of information is not there because of that no repeating theorem. Quantum information are not lost. So I guess uh, yeah, uh, maybe that like the choice of alpha, like it is the main thing that alpha 1 and alpha 2. So the claim was that basically they are not they have claimed, but they are not emphasized that for only for non-orthogonal state you can have the data masking. They have just said that in one line or two lines that you can have the data masking in case of non-orthogonal state. But I guess the the last condition that I have mentioned, this is the main that was the main condition that one has to follow, whether it is whether it is a non-orthogonal state or an orthogonal state. So if you are having a non-orthogonal state, you can have it you can use the you can Smith the you can make the orthogonal state and also have the data masking. So the main thing is you have to follow that the choice of alpha 1 and alpha 2. You have to follow that main. So it's not all about the choice of the state you are masking into, but it is I guess it is the main restriction is the choice of alpha 1 and alpha 2. Okay.
Okay. I don't see any more questions. So let's thank the speaker. And with that, we end today's session. So thank you, Shogo, again for the wonderful talk. So we will meet next week.